Hi everybody, we're going to be continuing our practice of reading a paper out loud as part of my camera ready process. As we get ready to publish a paper, I read through it out loud to catch any final errors, and in the interest of helping people who prefer to listen to papers or have trouble reading, I read the papers out loud and make it available to everybody. So without further ado, let's get started. Is automated topic model evaluation broken? The incoherence of coherence. Abstract. Topic model evaluation relies on automated estimates of topic coherence. Contemporary neural models surpass classical ones according to these metrics. However, topic model evaluation suffers from a validation gap. Automated coherence, developed for classical models, has not been validated using human experimentation for neural models. In addition, a meta-analysis of topic modeling literature reveals a substantial standardization gap in the use of automated topic modeling benchmarks. To address the validation gap, we compare automated coherence with the two most widely accepted human judgment tasks, topic rating and word intrusion. To address the standardization gap, we evaluate a dominant classical model and two state-of-the-art neural models in a systematic, reproducible way on two commonly used datasets. Automated evaluation distinguishes between models even when differences in human judgments are not significant. Section 1. Revisiting topic model evaluations. Topic models are a machine learning technique widely used outside computer science, including political science, social and cultural studies, digital humanities, and bioinformatics. Typically, topic model users are domain experts trying to identify global categories or themes present in document collections. This practice constitutes a human-computer assisted form of content analysis, also related to distant reading in literary studies. In general, topic models help humans understand large corpora. Evaluation of topic models has vacillated between automation and human-centered. While real-world users of topic models evaluate outputs based on their specific needs, the method development community has gravitated toward generalized automated proxies of human judgment to help inform rapid iteration of models. Initially, models were evaluated with held-out perplexity, but it disagrees with human interpretability. Consequently, the field adopted automated coherence metrics like normalized pointwise mutual information, a measure of word relatedness that does correlate with topic interpretability. The balance shifted towards automated coherence. Human evaluations have been abandoned by the method development community in the years since automated coherence metrics were adopted. In a thorough meta-analysis of contemporary topic model methods papers, none conduct systematic human evaluations. Instead, they rely solely on automated metrics for model comparison. However, current neural topic models are a far cry from the classical models that substantiated the original correlations. Manifestly, topics produced by neural models are often qualitatively distinct from those of classical models. This validation gap raises the question of whether automated metrics are still consistent with human judgments of topic quality. Moreover, we should always be cautious when extrapolating outside the range of data used to establish a relationship between models that established a relationship between variables. As an example, a neural model in Hoyle et al. Produces a much larger NPMI value than those used to determine human correlations in the original Lau study. The implicit assumption is that greater NPMI corresponds to more human interpretable topics. Finally, a myopic focus on a presumed proxy for human preferences can produce low-quality results. Does Goodhart's law, when a measure becomes a target it ceases to be a good measure, apply to automated metrics of topic models? Another challenge for automated evaluation, whether of classical or neural models, is widespread inconsistency. Researchers frequently fail to specify the information needed to calculate automated metrics or diverge from the practices that underpin human correlation. Furthermore, evaluation datasets, preprocessing, and hyperparameter optimization vary dramatically, even within a given paper. Our meta-analysis shows that the standardization gap likely limits the generalizability and reliability of topic model developers' findings. We address the standardization and validation gaps in topic model evaluation. 1. We present a meta-analysis of neural topic model evaluation 2. We develop standardized preprocessed versions of 2 widely used evaluation datasets, along with a transparent end-to-end pipeline for reproduction of results. 3. We optimize 3 topic models, 1 classical and 2 neural, using identical preprocessing, model selection criteria, and hyperparameter tuning. 4. We obtain human evaluations of these models using ratings and word intrusion tasks. And 5. We provide new evaluations of the correlation between automated and human evaluations. Our findings challenge the validity of current fully automated evaluations. Automated evaluation yields distinctions between models that corresponding human evaluations do not. Table 1. The first 3 columns are the highest NPMI topics for a classical topic model, LDA estimated via Gibbs sampling using Mallet. The next 3 are counterparts from a neural model, are DVAE reimplementation. Both models are trained on Wikitext with 50 topics, and NPMI is estimated over the top 5 words in each topic using a 4.6 document reference Wikipedia corpus. The mean top 5 NPMI over all topics is 0.156 for the classical and 0.256 for the neural model. Section 2. Topic modeling in perspective. Section 2. Topic modeling evaluation. Everybody loves automated coherence. A topic model is a probabilistic generative model of text that uses latent topics to summarize a larger collection of documents. The most influential variant, latent diversity allocation, assumes that the k latent topics are distributions over words, beta k, and the documents are admixtures over the topics, theta d. Users often evaluate model outputs globally, focusing on the most probable n-words of each topic, as well as locally by considering the most probable topics for each document. While techniques for topic modeling have progressed from variational inference to Gibbs sampling to deep generative approaches, the core goal discussed in Section 1, obtaining human understandable categories, remains central. The latest wave of methods, neural topic models, use continuous word representations and gradient optimization to fit parameters. These models claim to produce more interpretable topics than other models, including LDA. These claims are supported by improvements on automated measures of topic coherence. Section 2.1, NPMI, the standard topic model coherence evaluation. Like the concept of interpretability, that of real-world coherence is simultaneously important and slippery. We will not attempt to formalize it here, though see discussion in Section 7. For present purposes, the term has its roots in Latin cohere, to stick together, and we will think of coherence as an intangible sense available to human readers that a set of terms, when viewed together, will enable recognition of an identifiable category. Cheng et al. Show that perplexity, the original topic model evaluation, negatively correlates with human evaluations of topic. We review 2 human ratings of topic quality, direct ratings, and intrusion. Rating. Raters see a topic and then give the topic a quality score, conventionally on a 3-point ordinal scale. Intrusion. Cheng et al. Devised the word intrusion task as a behavioral way to assess topic coherence. The core idea is that when the top words in a topic identify a coherent latent category, it is easier to identify the words that do not belong to the category. Operationally, each topic is represented as its top words plus 1 intruder word, which has low probability of belonging to that topic, but a high probability of belonging to a different topic. Topic coherence is then judged by how well human annotators detect the intruder word. While many agree that the evaluation of Cheng et al. Is a noble goal, automated coherence's goal is to measure model quality without expensive, time-consuming human experiments. Lau et al. Show that, thankfully, some measurements correlate with human intrusion and rating scores. Because of that validation, the evaluation du jour is pairwise, normalized, pointwise mutual information, NPMI, which scores topics highly if the top n words, summed over all pairs Wi and Wj, have high joint probability of Wj, Wi, compared to their marginal probability. The sum of j equals 2 to n and I equals 1 to j minus 1 of the ratio, where the numerator of the ratio is the log of the joint probability divided by the conditional probabilities of I and j, divided by, in the denominator, the negative log of the joint probability of the words I and j. The probabilities are estimated using word co-occurrence counts from a reference corpus for a specific context window, which can range from 10 words to the entire document. As a result, the choice of reference corpus determines the strength of human correlation. A measurement is valid to the extent that it measures what it is intended to measure in the real world. Historically, automated coherence has been validated using human judgments from either crowd workers or experts. However, correlations based on classical models may not be applicable for NTMs. Our skepticism is motivated by theory, as neural word representations are intimately connected to NPMI, as is explicitly used by Altrius and Stevenson, and which produce similar NPMI scores as Lau et al. Levy and Goldberg showed that multiple representations create factorizations of PMI matrices. Topic models that have access to these rich representations could thus create topics with good NPMI scores without explaining the corpus well to a user. In contrast to classical topic models, no one, to our knowledge, has investigated the validity of NPMI evaluation for neural topic models. Given this lacuna, we conduct experiments aimed at validating that automated topic evaluations still correlate with human judgments of neural topic model quality. We compare against two common human evaluations of individual topic quality: direct rating and intrusion. Human evaluations, like automated topic modeling, lack standardization, which we address in Section 5. Table 2. Results of a meta-analysis of 40 neural topic modeling papers. Denominator may change as not all conditions are applicable. No recent neural topic modeling papers use human evaluations of coherence, and the metrics and models are difficult to replicate. Section 3, a meta-analysis of neural topic modeling. We analyze neural topic models research to assess the state of evaluation in contemporary topic model development. First, we take all references made by an existing comprehensive survey of NTMs, from which we select A, modeling papers which B, purport to be concerned with topic interpretability, and C, compare models' topics with an existing baseline. This yields 40 models, which all claim superior topic coherence. We examine data processing steps, hyperparameter tuning, baseline selection, and automated topic coherence calculations. Table 2 summarizes our results, and Table A1 enumerates the papers. Our analysis reveals variance in all areas. Pre-processing, which can significantly affect model quality and automated metrics, is often inconsistent across datasets within the same paper. When pre-processing is consistent, authors omit details necessary to fully replicate the pipeline. These issues imply that automated metrics for the same baseline and source datasets vary across papers. Compounding the problem, researchers often train their model on different datasets from those used to establish the relationships between human annotations and automated metrics. Dugan and Bunting find that the same metrics may not predict interpretability in new domains. Mirroring findings from Dodge et al., 40% of papers fail to clearly specify their model tuning procedure, often even the metric used for model selection. Calculation of automated coherence metrics is equally fraught. As discussed in Section 2.2, a complete specification for NPMI involves several pieces of information, including the reference corpus used to estimate joint word probabilities, the co-occurrence window size, and the number of words selected from the head of the topic distribution. 3 out of 4 papers fail to explicitly indicate the reference corpus. Even when we can assume the input corpus is used, it remains uncertain whether authors use, for example, a held-out set or the training documents themselves. For the 61% that specify the implementation of their coherence metric by pointing to a code repository or writing out the formula, some of these factors may still be in question. For instance, 6 authors reference Lau et al. And the supporting code, but the implementations are ambiguous. The original paper suggests a large corpus from the same source as the training data, but the repository script defaults to Wikipedia. In other cases, authors use bespoke implementations, which creates room for errors or deviate from the settings used in human experiments. For example, several papers use a document-wide context window with NPMI, which has not been correlated with human judgment. Lastly, even if automated evaluations are consistent, all claims of coherence improvement depend on the validity of results in Lau et al., generalizing to neural topic models. Section 4, closing the standardization gap for topic models. Our human evaluation of topic model output serves multiple purposes. A, establishing whether NTMs show improved coherence over a classical baseline, and B, reevaluating the efficacy and reliability of automated coherence metrics. In addition, a key goal is C, to provide a standardized pre-processing pipeline to support head-to-head comparisons as new methods are developed. We identify two commonly used datasets, which we in turn process using a standard pipeline. We then estimate topic models on each dataset following a computationally fair hyperparameter search. Our standardization efforts are similar to concurrent work by Tarragani et al. The main differences are that we A. mandate consistent pre-processing between training and reference corpora, and B. support multi-word expressions during vocabulary creation, see below, and C. support distributed hyperparameter searches. Section 4.1, Datasets and Pre-processing. Following Cheng et al., we use English articles from Wikipedia and the New York Times. For Wikipedia, we use Wikitext 103, and for the Times, we sample roughly 15% of documents from the LDC collection, making it an order of magnitude larger than Wiki. To compute reference counts, we use a 4.6 million document Wikipedia dump from September 2017 and the full 1.8 million document New York Times set processed identically to the training data. We use spaCy to tokenize and identify entities in the text. We create new tokens for detected entities of the form new _ York _ city per Krasnoshok and Jolie. Schofield and Mimno find that limitization in word simming can hurt topic interpretability, so we do not limitize. To maintain a roughly equal vocabulary size over datasets, we use a power law relationship of corpus size to rule out tokens occurring in fewer than a given number of documents. In addition to a standard stop word list, we define corpus-specific stop words as tokens appearing in more than 90% of documents. See Appendix 8.2 for complete details. We evaluate one venerable classical model and two newer neural models. Gibbs LDA. As a strong classical baseline, we use the widely loved Mallet implementation of Gibbs sampling for LDA. Mallet produces topics of qualitatively competitive quality to neural models. Dirichlet VAE. We re-implement Dirichlet VAE, a state-of-the-art neural topic model. For simplicity, we use pathwise gradients for the Dirichlet, rather than the rejection sampling variational inference of the author's primary variant. Dirichlet VAE is a wholesale improvement on the first successful neural topic models, the popular Prod LDA, and is competitive against recent models on automated coherence. The generative model is simple and retains a broad similarity to LDA, the difference being that it does not constrain. The primary difference is that it does not constrain the estimated topic word distributions to the simplex. ETM. Thanks to their improved flexibility, many neural topic models incorporate the use of external word representations on the premise that large-scale general language knowledge improves topic quality. The embedded topic model is a popular neural topic model that relies on word embeddings in its generative model. We maintain a fixed computational budget per model following the exhortation of Dodge et al., and use a random set of 164 hyperparameter settings across datasets for each model type. We train models for a variable number of steps, a hyperparameter, to calculate automated coherence for the model. We use the topics produced at the last step. For human evaluations, we select the models that maximize NPMI, estimated using the reference corpus with a 10-word window over the top 10 topic words. We follow the recommendation of Ding et al. And learn skipgram embeddings on the training corpus for ETM. Experiments with external pre-trained embeddings did not yield substantially different results. As in Hoyle et al., we eliminate models with highly redundant topics, a known degeneracy of neural topic models. A. Models in which any of the top 5 words of one topic overlap with another, and B. Models that have a topic uniqueness score above 0.7. Ranges for hyperparameters and other details are in Appendix A.3. Section 5. We use the ratings and word intrusion tasks from Section 2.2 as human evaluations of topic quality. We recruit crowd workers using Prolific, an online panel provider, and collect data with the Qualtrics survey platform. We compensate workers $2.50 per rating survey and $3 per word intrusion survey, prorated based on a mean completion time in a pilot study at a pay rate of $15 per hour. The criteria for selecting the number of participants is unspecified in previous human evaluations of topic model coherence. However, Card et al. Showed that many NLP experiments, including those relying on human evaluation, are insufficiently powered to detect model differences at reported levels. Adopting a straightforward generative model of annotations, we select enough crowd workers per task to ensure sufficient statistical power. to obtain significance at alpha equals 0.05, resulting in a minimum of 15 crowd workers per topic for both tasks. On this criterion, both Chang et al. And Lau et al., with 8 annotators, are underpowered. For each of our 2 datasets, we generate 50 topics each from the 3 models in section 4.2. In the word intrusion task, we sample 5 of the top 10 topic words plus 1 intruder. For the ratings task, we present the top 10 words in order. We separate the datasets for each task and randomly sample 40 of the 150 topics to present. In the ratings task, we include an additional 16 synthetic poor quality topics to help calibrate scores and filter out low quality respondents. Phrasing of questions closely follows the wording used by Chang et al., and crowd workers receive detailed instructions with examples before responding to items. As topic contents can be esoteric, we ask crowd workers about their familiarity with the words in each question. We speculate that this question can help protect against spurious low scores for otherwise coherent topics, as real-world users of topic models are familiar with domain-specific terminology. Figure 2. While automated evaluations, here in PMI, suggest a clear winner between models, human evaluation is more nuanced. Human judgments have greater variability over a smaller range of values. Colored circles correspond to pairwise one-tailed significance tests between model scores at alpha equals 0.05. For example, the rightmost orange circle at the bottom right shows that human intrusion ratings for DVAE are significantly higher than ETM for topics derived from Wikipedia. Figure 3. Mean human evaluation on the ratings and word intrusion tasks after filtering out respondents who reported a lack of familiarity with the topic words. When filtering, DVAE scores improve, highlighting its tendency to produce esoteric topics. Section 6. Human judgment differs from automated metrics. We compare human judgments to automated methods on topics derived from using our 3 models. Section 6.1. Human assessment. To establish model differences using human ratings, we use pairwise significance tests, a proportion test for intrusion scores, a U-test for the ratings, and a T-test for automated metrics, using one-tailed tests for each pair in both directions. Although DVAE fares better on the intrusion task, evaluation using respondent ratings favors GLDA. Respondents report familiarity with terms over 90% of the time on both the intrusion and ratings tasks for both GLDA and ETM. However, DVAE has notably lower average term familiarity in both tasks at 70%. This difference suggests that the topics selected by DVAE are narrower in scope than those of the other models. As shown in Figure 3, removing item annotations where respondents indicate unfamiliarity causes performance for DVAE, accuracy in the word intrusion task, and the ratio of terms rated as very related in ratings to increase to the highest of all 3 models. Our human evaluation results are consistent with past iterations of the ratings and word intrusion task for topic models. Mendo et al. Report an average of 2.36 on the ratings task on a dataset of medical paper abstracts. Our rating means are 2.5 to 2.8 across all variations. Our word intrusion means range from 0.7 to 0.8, which is comparable to the roughly 0.8 accuracy on the LDA model in Chang et al. Median time taken on the task was 8 to 9 minutes. Following Altrius and Stevenson, we calculate inter-annotator agreement with the mean Spearman correlation between each respondent's score per topic and the average of other respondent scores, obtaining a value of 0.75. CF, their value of 0.7 on the New York Times corpus. Additionally, we include synthetic poor quality topics, footnote 15, correctly identified by annotators, and we monitor the duration taken for the survey to hedge against insincere submissions. Section 6.2, Automated Metrics. NPMI declares DVAE the unequivocal victor among the 3 models, with Gibbs LDA a clear second. A different story from the human judgments. To understand the relationship between automated metrics and human ratings, we estimate the Spearman correlation between the 2 sets of values for each task and dataset for several metric variants. Although previous studies have used mean human ratings over topics, this decision obscures the inherent variance of the human ratings and leads to overconfident estimates. We therefore construct 95% confidence intervals by resampling ratings with replacement equal to the number of annotators per task. We estimate NPMI with the standard 10-word window and CV with the recommended 110-word window. The Wikipedia corpus appears to be best correlated with human judgments, even for the models trained on the New York Times corpus. This contradicts Lau et al., where within domain data have the highest correlation. While all correlation coefficients are statistically significant, the strength of the correlation alone does not justify their use in model selection, as is standard in the neural topic model literature. In particular, the inherent uncertainty of human judgments means that it is difficult to determine when an increase in a model's mean automated coherence implies a significant improvement in the corresponding human scores. As noted above, automated metrics exaggerate model differences compared to human judgments. To help clarify the utility of automated metrics for model selection, we ask how often an automated metric incorrectly asserts that one model is superior to another. To do so, we generate a bootstrapped estimate of the false discovery rate of each model. First, for each dataset, we randomly sample two independent sets of k equals 50 topics without replacement from the original pool of 150, along with their corresponding automated and human scores, resampled with replacement, as in Table 3. Treating the two sampled sets as outputs from two different models, we compute pairwise significance tests between each set for both the k automated metrics and the k by m human scores, using a proportion z-test for the intrusion scores and t-test for all other values. After repeating this process for 1,000 iterations, we report the proportion of times a significant difference is detected using the predicted scores despite equivalent human scores, after correcting for the probability of type 1 errors, alpha equals 0.05. Even the best performing automated metrics predict significant differences absent a meaningful human effect roughly 1/5 of the time. These results suggest that automated metrics alone may be inadequate for model comparison. Table 3. Spearman correlation coefficients between mean human scores and automated metrics. Underlined values have overlapping bootstrap 95% confidence intervals with that of the largest value in each row. Concatenated refers to correlations computed on a concatenation of values for the New York Times and Wiki items. Val is a small held-out set of 15% of the training corpus. Using the more data-appropriate logistic and ordered probit regressions for word intrusions and ratings data leads to somewhat different conclusions about relative metric strength. CIs are estimated using 1,000 samples. Table 4, false discovery rate, 1 minus precision, lower is better, and false omission rate of significant model differences when using automated metrics. Automated metrics often overstate meaningful model differences. Bolded values are those with the lowest geometric mean of false discovery rate and false omission rate. We sample two independent sets of 50 topics along with their human scores and automated metrics. These sets act as the outputs of two models. We then compute significance tests between sets per figure 2 on both the automated scores and human scores. A false positive occurs when one set has significantly larger automated scores despite no meaningful difference in actual human scores. Estimates are over 1,000 samples. Section 6.3, explaining the discrepancy. One reason for the discrepancy between human judgments and automated metrics is that metrics favor more esoteric topics. Specifically, there is a significant negative correlation between a topic's NPMI and the share of respondents reporting familiarity. However, even after filtering out respondents who are not familiar with topic terms, automated metrics still overstate model differences. Qualitatively, this is apparent when examining topics with a high PMI, but humans rate poorly. In Table 5, the top rows consist of financial terms that frequently appear together in New York Times articles, and the second row contains rare terms about boating. Arguably, both are reasonable topics for their respective corpora. We can also see instances where words are qualitatively very related, bottom half of the table, but NPI fails to score adequately high, perhaps because these words, while related, may not frequently appear together within a 10-word sliding window. The table also reveals problems with human evaluation. The third and fourth rows are topics that correspond to real estate listings and obituaries, which contain the words that, devoid of context, may appear unrelated, taxes, and bedroom. While this affects the rating somewhat, it renders the word intrusion task much more difficult. The problem with topic model evaluation may extend to our choice of human evaluations as well. Table 5, topics with the largest human NPMI discrepancies. Top half are topics where NPMI is high and human preferences are low. Bottom half is the reverse. The top two rows in each section have a high ratings human difference. NPMI is calculated with a 10-token sliding window over the reference corpus. Rating is the average 3-point rating for a topic, and int refers to the percentage of annotators who identify the intruder word correctly. Section 7. So, is automated topic modeling evaluation broken? Topic model evaluation, both human and automated, requires re-evaluation. We agree with Dugan and Bunting, who write that coherence measures designed for older models may be incompatible with newer models. and instead argue for evaluation paradigm centered on corpus exploration and labeling. The right starting point for this reassessment is the recognition that both automated and human evaluations are abstractions of a real-world problem. The familiar use of precision at 10 in an information retrieval, for example, corresponds to a scenario corresponds to a user only willing to consider the top 10 retrieved documents. In future work, we intend to explore automated metrics that better approximate the preferences of real-world topic model users. One primary use of topic models is in computer-assisted content analysis. In that context, rather than taking a method-driven approach to evaluation, it would make sense to take a needs-driven approach. Generic evaluation of topic models using domain general corpora like New York Times needs to be revisited, since there is no such thing as a generic corpus for content analysis, nor a generic analyst. Content analysis can be formulated in a broad way, as Krippendorf has shown, but its actual application is always in a domain, by people familiar with that domain. However, general corpora and crowd worker annotation are used in practice. We have identified coherence as calling out a latent concept in the mind of a reader. But who are the human readers and what conceptual spaces matter to them requires further thought.